Now we know how the controller generally works. Let's assemble all these ideas together. So if you take a look at a block diagram for the controller, you'll see something like this. So what we have is we have the controller. It just have the finite state machine in it. It has the custom logic to actually control the output, and this output is actually connected to the I2C bus, whether it's serial data or serial clock. And we have about four inputs and four outputs. So let's talk a little bit about these inputs. So the first one is actually right into the I2C. It basically just write whatever you put on the command, whatever you put in DN into internal registers to store them. So what is command? Well, command is actually the signal that we use to move between the different states and to start certain actions. And generally, we have actually a start, a write, a read, a stop, and a restart. Because we have 5, we need 3 different bits or 2 encoded. And these are basically the codes we're going to be using. So that command is actually a 3-bit signal. So whenever you assert that write I2C, is you're just writing that into some sort of an internal register. And at the same time, you're writing another value, which is in here. It's actually the byte you want to send. It's the DN. If you want to send something over the bus in here to a slave, you basically have to put it in here. So whenever you assert that, both of these values will be written into some sort of internal registers in here. The divisor is pretty straightforward. It's similar to what we've seen before. It's actually to control the I2C clock frequency, and it's generally speaking that value is utilizing some sort of an equation that you implement in the driver. Okay, so let's take a look at the output. The output are also pretty straightforward. I have an 8-bit output. This is the one that if a slave actually wrote, or a device you actually read from it, it's actually and you want to get it, this is basically how you just route it out of the controller. And acknowledge is just a single bit from a slave. It's coming from a slave all the way in here, that basically it acknowledges receiving something that you sent it. The ready signal is that signal that tells me that the controller or the finite state machine, the one in here and the one in here, is ready to do something, whether it's in idle or whether it's in the hold state. I can just read that. And the done tick is a little tiny tick that appears every single time you finish sending a byte or receiving a byte. And that's how we're going to implement it. So the HDL code, if we take a look at it here, it's pretty straightforward. It's a pretty straight implementation of this particular finite state machine. So if you take a look at it, it's a really long file, and you can read it on your own because it's pretty straightforward. What I want you to pay attention to is the following. There's a few registers, you can figure them out in here. Some called quarters, some half, and if you take a look at the quarters and the halves, they're basically based on the divisor. So the quarter is a divisor, the half is actually just I just zero out that particular here. Basically I'm shifting it so I get half of it. It's the same thing as the divisor, okay? The quarter isn't the divisor. Anyway, all of these are when you go through the state machines, you'll see that I have the idle state, the start start to state. And in each one of these states, I'm comparing it to something called the C-reg, and that's basically the counter that's actually counting. If it reaches that half, that means I have moved half a period, and then I zero out that counter and I start again and I move to a different state. Again, follow these. This code is really straightforward implementation of the diagram that we've seen before. What I'm more interested in is the following codes in here. The first one is this. Okay, so in the module, I have a couple of new data type we haven't seen before, which are basically the try. It's actually try, it stands for tri-state, so it could be either 0, 1, or 0, or 0, 1, or Z, which is high impedance. And more interestingly is actually the SDA, the serial data, is actually an in and out because it's bidirectional, so it could be an input or it could be an output. So these are two interesting things. And in terms of code, the one that I really want to take a look at is actually these few lines in here, basically between here all the way to that. Let me just go to the slides and just make them a little bit bigger so that I can talk a little bit about them. Okay, so in here I have just captured these particular few lines of code because these are the ones that implement that custom logic that tells me what to do with the output, whether it's the serial data or the serial output. This is actually the output control logic. This is how it's implemented. So it's implemented. Let's talk a little bit first about the SDA, okay, and then we'll talk about the clock. So in the SDA, what we do is we're going to create some sort of an intermediary signal. We're going to call it into, and into stands for the following. If you're writing into the receiving register, basically you're receiving something, okay? So you're writing into the receiving register. Okay, so when that happens, well, it happens in the following. If you are in a data phase, you're sending a data, and the way you know it is from the finite state machine. So this is this line in here. And the command is actually read, okay, because you are reading and you know it from the command. So it's actually this line in here. And it just happened that your bit register, okay, is less than 8. Basically, you're still not done receiving these 8 bits that you have. And you usually get it from the finite state machine in here as well. So if you're in that case, what I really want to do is, this is actually writing into that RX, and I do care about it. So what happens is you should actually just disconnect this particular tri-state buffer in here, and we'll see how that happens. Another reason why you want that tri-state buffer to be disconnected is actually when you care about an acknowledge bit. You want to receive an acknowledge bit, and the way you receive the acknowledge bit is actually after you write into the master. So you'll see that you're in the data phase, but now you are writing into the master. Again, the data phase, you can get that it's from here, you know that it's writing from here, and you know that the bit register now is the number 8, which is basically the 9th bit in the 9th clock cycle, and you know it usually from the finite state machine. If that's the case, this should be disconnected so you can receive the acknowledge bit and put it in here. So into just tells me, well, I am receiving something from a slave into the master controller. Okay, so now let's take a look at the second line here. The second line is actually relevant to this idea of the in, out, and the try. Okay, so what it tests, am I writing into the receiving register? Okay, if I'm writing into the receiving register, I need to disconnect this guy. Do I want the data line to be asserted? This is what this stands for. Okay, so if it is 1, basically, if you think about it, if this is 1, I want this to be disconnected. Or if this is 1, I want to be this disconnected. Basically, SDA register, if you want it to be 1, that means you want this to be 1. And why would I disconnect it? Because by default, it's 1. You don't need to send it a 1. It's by default because it's raised through pull-up resistors. Okay, if that's the case, all you need to do is just disconnect that. That's basically what that BZ is. It actually tells me, hey, disconnect that tri-state buffer in here. Other than that, if you're not writing into, okay, and you are trying to send a 0, what you need to do is actually put a 0 in here. And that's basically how you do it. So if you have a 0 in here, you're basically just connecting that buffer. So you're only connecting the buffer when you're actually sending an actual 0 in here. Okay? And similarly, we can take a look at this S clock, which is basically the serial clock, and it's exactly the same idea. So if I want it to be 1, all I have to do is just disconnect it. And if I want it to be 0, I'll have to put a 0. And that's pretty straightforward. And that's how this HDL is implemented. Of course, the finite state machine is also implemented in that HDL.